Hello BC Calculus students, this is Mr. Johnson and this is section 2.3, which is on the main limit theorems. The opener here is the question, what is a limit, which we did in our last section, and a limit as a short explanation is a y value. And so our definition of a limit, if we have x approaching a of a function f of x and we say it's equal to L, that means that this limit, as you analyze x approaching a from both the left and the right, has a function value, a y value of L. The conditions for a limit to exist are that both the left and the right limit are equal. So if we approach a from the left side of f of x, it is equal to the limit as we approach a from the right side of f of x. When this occurs, we say that the two-sided limit exists. And that two-sided limit is the same as what the left and the right are. So we have just kind of an overview here of the conditions of a limit as well as what a limit is. Below we have the properties of limits, which you've seen in AB calculus, and the key to all of these limit properties are that each limit must exist. So when you analyze the limit of f of x as x goes to c and it equals L, and the limit as x goes to c of g of x and is equal to k, that's the only way that these limit laws will exist. If either one of these limits did not exist or they both didn't exist, you couldn't apply any of these properties. With AP, they have very clever ways of testing this, and we'll be showing you those throughout this chapter as well as the school year. But you just got to keep in mind that you can't apply one of these limit laws unless they both exist. All right, let's move to the next page. Okay, so what we'll do here is we'll just look at the idea of these limit laws and about how limits do exist. We'll also look at the left and the right limit. So what I would propose is that you pause the video and you try these 8 problems and see if you can get some of these on your own, and then maybe come back and then you can watch the remaining portion here as I work through the examples. So for number 1, we have the limit as x goes to 2 of f of x, and of course this is a piecewise function, as you can see by the graph. So I'm going to look at the limit from the left, and it looks like it's going to be 0, and then we'll look at the limit from the right, and that looks like it's 1. And so what we could say here is that this particular two-sided limit does not exist because the left and the right limits do not equal each other. Let's look at number 2. Number 2 is the limit as x goes to 2 of g of x. G of x is a similar situation where we have this piecewise graph. So we have the limit as x goes to 2 from the left side of g of x, and that looks like it's 1. And then the limit as x goes to 2 from the right side of g of x, and that looks like it is 0. So because the left and the right limit are not the same, then this two-sided limit does not exist. Okay, let's move on to number 3. So for number 3, we have the limit as x goes to 2 of h of x. Now with h of x, we have this rational function, so we're going to look at what happens if we were to substitute in 2. I'm just going to kind of analyze this by observation here. So we have 2 squared minus 4, that's going to be 0. We have 2 minus 2, that's 0. That's an issue. So what we need to do is simplify this algebraically. And I'm going to go through some of this in later examples. But in this particular case, we have the limit as x goes to 2 of x plus 2 times x minus 2 divided by x minus 2. If you were to cancel that factor, you would have the limit as x goes to 2 of the quantity x plus 2, which gives us a limit of 4. So this one finally exists. Then we have the last one, which is going to be number 4. That's going to be the limit as x goes to 2 of j of x. And since j of x is in parts as well, we're going to look at the left of 2, which is going to be 1. And then we'll look at the right of 2, or as x approaches 2 from the right, I should say, of j of x, and that's going to be negative 1. So just like number 1 and 2, this limit does not exist because the left and the right limits are not equal. Okay, so we have these 4 different situations, these 4 graphs, equations, and 3 of the 4 have limits that do not exist. Now what we're going to do is we're going to look at some of the properties of limits. The first one is going to be number 5, where we're looking at the addition property of limits. Now the property says that we can take the limit of this sum and we can look at the limit of g of x and we can simply add it to that of h of x. However, the condition is that both limits have to exist. Now if you look up at the problem of the problems and you look at the limit as x goes to 2 of g of x, it does not exist. The limit as x goes to 2 of h of x does exist. Just because one of the two does not exist, that means that we cannot simply apply this property. That doesn't, however, mean that this limit automatically does not exist. So just because the limit as x goes to 2 of g of x does not exist, we can't automatically assume that therefore the sum does not exist as well. So what we need to do is we need to look at the left and the right. Now we can do this because both limits or both functions have a limit from the left of 2 that exists. So we can apply the limit laws. When we look at the limit as x goes to 2 of g of x, we get 1, that exists. The limit as x goes to 2 from the left of h of x is 4, that exists. Therefore, we have a limit of 1 plus 4, which is 5. So the left side of the limit does exist. Now we're going to look at the right side of the limit. So we have x approaching 2 from the right of g of x plus h of x. And from the right side, g of x has a limit of 0, that exists. H is still has a limit of 4, that exists. And so we take 0 plus 4 and we get an existing right-sided limit. The problem is that because the left and the right do not agree, this does not exist, and it's because of that analysis. Okay, let's take a look at number 6. So for number 6, we have the limit as x goes to 2 of f of x plus j of x, and f of x does not exist, and the limit as x goes to 2 of j of x also does not exist. Again, we cannot assume that this limit then automatically does not exist. However, it may. Let's take a look at the left side first. So the limit from the left of 2 of f of x is 0, and of j of x is going to be 1. So we have 0 plus 1, so that limit is going to be 1. Then we have the limit as x goes to 2 from the right side of f of x plus j of x. And we can look up here at f, and the limit from the right is 1. And the limit from the right of j of x is negative 1. So we have 1 minus 1, and we get 0. So as you can see, these limits do not agree, and therefore this limit does not exist. So my guess is that you're beginning to think that if we do have a situation where we combine certain limits or certain functions within a limit, and one of those functions has a limit that does not exist, therefore the total does not exist. That often is the case, but not always. So let's take a look at number 7. We have the limit as x goes to 2 of f of x times g of x. Again, f of x, that has a limit that does not exist, as well as g of x. And so we have the situation again where we have two functions that have limits as x goes to 2 that do not exist. But we're still going to look at the left first. So we have for f of x a limit of 0, and for g of x we have a limit of 1. And we're going to multiply those together. So we have 0 times 1, which is 0. Then we're going to look at the limit from the right of 2, and for f, that value is 1, which is here, and for g of x, that value is 0. So we have 1 times 0, which is 0. And all of a sudden, in this case, we actually have a left limit and a right limit that agree, and therefore number 7, even though individually they were non-existent limits, as we apply this multiplication and as we look at the left limit and the right limit, we can see that for number 7, that limit as x goes to 2 of the product of f of x and g of x is 0. And then our last one is number 8. And we're going to do the same thing. We're going to look at the left side first of f of x times j of x. And the limit for f of x we saw was 0. For j of x, it's 1. So we take 0 times 1 and we get 0. And then we have the limit as x goes to 2 from the right of f of x times j of x. And for f of x, from the right side, it's 1. And for j of x, it's negative 1. And so we get 1 times negative 1, which is negative 1. So these two do not agree. Therefore, that limit does not exist. Okay, so what I hope that you see from this is that certain patterns occasionally will come out when you talk about limit properties and whether or not a limit began as a non-existent limit. But again, you can't assume everything, because as we saw in number 7, there was actually an existent limit that came out of number 7 while the pieces of it were non-existent. And so we can't always assume things about limits intuitively, because it might be a little bit misleading. Okay, let's go on to the next page. All right, so for the next page, we have our limit laws, the one-sided limits that we've talked about, and the two-sided limits, and how you need the one-sided limits to agree in order for the two-sided limit to exist. And so you can see just the theorem that's listed up there. They call it Theorem 3 in our notes. And then we also have Theorem 2, the polynomial and rational functions. And you can read through those. But again, what they're talking about with polynomial and rational functions is that that your limit itself, as long as it's in the domain of a rational function, will exist as a substitution. And we'll talk a little bit more about that towards the end of this particular section. So we're going to try these two problems, number 9 and 10, and these two problems are common. They'll come up in some of the curriculum that we've seen from AP, but they're dealing with the absolute value graph. And one of the reasons why they use this graph is because of the sharp corner that's caused with the absolute value function at the origin. And so we're going to use the definition of the absolute value function that we've already talked about, where you have x if x is greater than or equal to 0, and you have negative x if x is less than 0. And so when we look at this limit, we're going to basically try to prove that the limit itself as x goes to 0 of the absolute value of x is 0, aside from just simply substitution. And so we're going to look at the limit from the left. So as x approaches 0 from the left, and our function, if we're approaching from the left, is simply just negative x. And by direct substitution, utilizing the idea of the theorem above with polynomials, is that since negative x, so let me back up, the absolute value of x is not a polynomial. So what we do here with a piecewise function is we turn it into a polynomial. And when we turn it into a polynomial, then when we look at negative x and we know that it's a polynomial, we can use this theorem to use direct substitution and say, okay, well, I'm going to plug in 0 and I get 0. In a similar way, we're going to look at the limit as x approaches 0 from the right side, and based on our piecewise definition, that is simply just x. And for similar reasons, we have a limit of 0. And so we can conclude, because the limit from the left and the limit from the right are the same, then the limit as x approaches 0 of the absolute value function of x is 0. We'll take sort of a similar approach here in example 10, except the function's a little bit different. So we're going to utilize our definition of the absolute value function again. However, this time, when we look at the limit from the left, it's going to differ from the limit from the right. So if we're approaching 0 from the left, based on our definition of the absolute value of x up here, we have a polynomial equation y equals negative x. So the numerator is negative x. The denominator is x in the original problem, and that's not going to change. That doesn't need to change. And what we have here is a rational function. Now the problem is that if we were to substitute 0 in for x, we have the situation where we have 0 in the numerator, 0 in the denominator. So instead of substitution right away, we're going to simplify. And we get negative 1 for a simplification. And of course, we don't need to substitute 0 in anywhere because there's no input value, and we simply just get -1 for a limit. Then we can take a look at the limit as x approaches 0 from the right side. In this case, based on our absolute value definition in red above, we would have x in the numerator. We still have x in the denominator. We want to simplify this down, so we get 1. And of course, the limit as x goes to 0 from the right of 1 is 1. Because these two limits, so first from the left of -x over x, is not equal to the limit as x goes to 0 from the right of x over x, we could say that the limit as x goes to 0 of the absolute value of x over x does not exist. All right, let's go to the next page. On this page, we're going to talk about the squeeze theorem. Now, in the past, this has been new for you all. It might feel new today, I don't know, but you did technically learn this in AB calculus because this is sort of a new addition to the AB calculus curriculum. We've been doing it for a long time in BC, but I want to walk you through the squeeze theorem again and just make sure that it makes sense visually, and then we will utilize this off and on throughout the year. It's not one of the problems that's going to be very common when it comes to limits, but I do expect them to throw it in somewhere, maybe even a free response question. So let's say that we have some function h of x, and let's say we have some function g of x, and a third function f of x. Okay, so the theorem says, and you know what, I'm going to pause and write it out and then I can talk about it. Okay, so here's the formal definition. So if we have this sort of this situation, this picture that I drew, and if g of x is less than or equal to f of x, which is less than or equal to h of x, for all x values within a particular x value, we just call this c. And if the limit as x goes to c of g of x is equal to the limit as x goes to c of h of x, and it's a value L, then the limit as x goes to c of f of x is also L. Now visually we should be able to see this, and here's where L is, right about there. So we should be able to see this on this graph, is that we've sort of squeezed f in between g and h for a small period of time. So obviously f is in between h and g here, but it's not very close together, so we really wouldn't be able to prove much over here. But in this little region, it's so squished together that we've been able to prove, since both g and h have the exact same limit value at a certain value as x approaches it, then f of x will have a same reaction, or f of x will react in the same way. So let's try this example below and see if we can use the squeeze theorem to think about this. With trigonometry, one of the most common things is to utilize the idea of sine and cosine being between -1 and 1. So that's often what we're going to look for with sine and cosine. There's obviously other situations that this will come up in. But what we could do, based on our knowledge of sine and cosine, we could say that sine of 1 over x, no matter what x is, at most will be 1, and at the least will be -1. So just think about that for a second. No matter what x is, the output of sine is going to be between -1 and 1. If this is the case, algebraically, we're going to multiply every single one of these elements by x squared. So we have -x squared is less than or equal to x squared times sine of 1 over x is less than or equal to positive x squared. Now, why would we do this? Well, we're trying to get this particular function that we're analyzing in the middle, in the unknown aspect of the squeeze theorem. So in other words, we have something on the left side, something on the right side of the compound inequality that we're well aware of. We know, because it's very simplistic, that the limit as x goes to 0 of negative x squared is the same thing as the limit as x goes to 0 of x squared, which is simply just 0. We know that. That's obvious. That's easy. It's by substitution. It's a polynomial, so it fits our theorem on the previous page. We can by substitution just analyze this. Well, if that's the case, and so we have two things here. If this is the case with our limits, and this is the case with our compound inequality, then it follows that the limit as x goes to 0 of x squared sine of 1 over x is also 0 by the squeeze theorem. So that's one of the examples of how the squeeze theorem is used. AP has also done a very good job of using sort of these arbitrary functions that we don't know the equations of, but we know characteristics of, to utilize the squeeze theorem. So just pay attention for that too. We will continue to practice with you and give you examples with regard to the squeeze theorem. Okay, we're going to go on to the next page, and I'm going to show you just a couple more algebraic examples of evaluating limits. So if you jump in your notes to page 17, that will be our next page. Okay, so here we are on page 17, and what I'd like to do is just highlight a couple of your homework problems. The reason for this is that I want to make sure you remember from AB calculus that when you evaluate limits, there's sort of four different outcomes. I mean, obviously we have other aspects to evaluating limits, but one of the outcomes when evaluating limits is that you substitute in the value and you simply just get a number like 4 or 8 and you're all done. It's a very simplistic limit. We probably won't experience one of those on the exam, but we'll look for it because if you can just simply plug in a number and get a limit, you're done. You have no work to do. Number 2 would be something like 0 divided by a number. For whatever reason, we sort of react to this differently. We think that, oh, there's a 0 there. There must be something going on. No. 0 divided by 10 is 0. 0 divided by 20 is 0. As long as that denominator is not 0, then this is simply just a limit of 0, which is just as easy as number 1, but for whatever reason we get a little confused by that. So number 1 and 2 here are great outcomes because they're really simple for us to deal with. Number 3 would be some sort of number other than 0 divided by 0. So 10 divided by 0, 4 divided by 0, a million divided by 0. Okay, in those cases, we are going to get a limit that does not exist. Now, we may have to identify whether it's a limit approaching infinity, whether it's a limit approaching negative infinity, but that's sort of dependent on the problem itself. This could be a little bit more work for us, or it could be really straightforward because if we can identify a proper limit that is a number over 0, 1 over 0, let's say, then it would be a non-existent limit. That may be our answer on a multiple choice question, and we would be done. Okay, so number 4 is the one where we have to do a lot of work, and this is the one that you're going to get most often on the exam itself, and that is when you get, let's say, 0 divided by 0. Don't ever write it that way, by the way. I'm just notating this. If you wrote that on the exam where you actually did 0 divided by 0, how I've written it, you will lose credit. We will work with you, especially when we start to do L'Hopital's rule, on how to write all of that stuff. You need to separate the limit of the numerator, separate the limit of the denominator. I'm just showing you a quick shorthand of what we're looking for. If you get 0 over 0, you get infinity over infinity, you get negative infinity over infinity. Those are all situations where naturally we're going to use L'Hopital's rule to evaluate as our sort of our first go-to. I want to show you the other techniques beyond L'Hopital's rule right now. So L'Hopital's rule we're going to tackle when we start doing some more stuff with derivatives. But for right now, I want to show you just a couple examples of how to deal with number 4 on this list using algebraic techniques, which are also really helpful. So number 18 is one of the ones I want to do, and I'm just going to do a couple problems from your homework. I want you to work on the rest. In this case, if we were to substitute 0 in for h, we would get 1 minus 1, which is 0, and that denominator h would also be 0. So this is a situation where we need to manipulate it. Again, we could use L'Hopital's rule. I'm going to take the approach of using some other algebraic techniques. This one is called using the conjugate. And the conjugate will look in this problem like this, the square root of 1 plus h plus 1. And we'll do the same thing for both the numerator and the denominator. So when we apply the conjugate, we have the limit as h goes to 0. The numerator, if we were to distribute the conjugate to this entire fraction here, we would get 1 plus h minus 1. The beauty of the conjugate is that the middle terms will cancel. And then we get h times the quantity 1 plus h, square root of 1 plus h plus 1. Then we would want to simplify the numerator, so we would have just simply h. Then we want to cancel the h in the numerator and the denominator. So we are left with 1 divided by the square root of 1 plus h plus 1. And finally, we're going to substitute in 0 again, now that we've done our algebraic manipulation, and we get 1/2. And that's going to be our limit. Okay, number 19 is another one that I wanted to point out. Number 19, same kind of thing here. If we substitute in x is equal to negative 4, we get 0 and 0, and so we're stuck with some issues here. So what we're going to do here is a technique called clearing the fraction, where we're going to multiply by the product of denominators. In that, in the numerator there, you have two different fractions that are being added. One denominator is 4, one is x. If we multiply by 4x, we actually clear all the fractions in the numerator. So we'll have the limit as x goes to negative 4. And if we take 1/4 times 4x, we get x because the 4's cancel. And then 1 divided by x times 4x, we get 4 because the x's cancel. In the denominator, we have the quantity 4 plus x times 4x. As you can see, you can cancel the x plus 4 in the numerator and the denominator. So we have the limit as x goes to negative 4 of 1 over 4x, and our limit is negative 1 over 16 when we substitute in, negative 4. Okay, I'm going to do number 22 as well, and the reason for this is that I want you to make a connection to the properties we talked about, and make sure that you understand that when we look at a situation like this, and we take a look at just the limit as t goes to 0 of 1 over t, it is 1 divided by 0. Remember, that was one of the ones that we were just talking about. That's a non-existent limit. Well, because of this, we can't actually answer the question because this particular limit does not exist. This one over here also happens to not exist. And so therefore we can't subtract them, because remember, the only way that we can subtract a limit like that is if both limits individually exist. So due to this, we're going to need to use some algebraic manipulation here. We're going to have to look at what can we do to combine these and get rid of that subtraction. So we're going to look at combining denominators like you did way back in elementary school. I'm going to multiply the first fraction by t plus 1, both top and bottom. And the reason for that is that in the denominator on the second fraction, if you factor that, you would have t times the quantity t plus 1. And in this case, now I can combine them through subtraction. And if you combine them, you get t divided by t times the quantity t plus 1. The t's can cancel, leaving you with 1 over t plus 1. And if t approaches 0, you get a limit of 1. Okay, I'm going to do one more problem with you on the next page. In your book, this is page 21. So if you just want to skip ahead to that, the problem I want to do for you is from 2008. It's number 5. And this is one in which if you substituted in 0, you would have 0 in the numerator, 0 in the denominator, and it would be a L'Hopital candidate. However, you'd have to do L'Hopitals on this problem a handful of times. And so this is one of those examples where L'Hopital, the technique does not fail, but it probably takes you more time than simple factoring. So if you were to take this limit as x goes to 0 and factor an x squared out of the numerator as well as out of the denominator, I think you'll save yourself a lot more time than doing L'Hopital's rule. In this case, we can cancel the x squareds. So we get 5x squared plus 8 in the numerator and 3x squared minus 16 in the denominator. So if you substitute in x is equal to 0, you get 8 divided by negative 16, and so your answer here is A. And it's a pretty quick factoring process versus L'Hopital's rule, which I said was, maybe 2 or 3 times in a row. Okay, that's section 2.3. We'll move on pretty soon here to section 2.4. Thanks.